Hello, everyone. Thank you for joining us today. It's noon here in the Midwest, so we're going to go ahead and get started with today's broadcast. My name is Kelsey Cervantes. I'm a marketing manager here at Zerus. I'm really excited to share with you our topic and our speaker for today's webinar. A quick housekeeping note, like most webinars do, you'll notice a section of your screen where you can submit questions. Please feel free to do that if something piques your interest during the presentation. I will read those questions live to Tyler at the end of today's broadcast so you can get those questions answered. So let's dive into today's topic, results over hype, gain actionable AI insights today. People have been talking about machine learning and AI for a few years now. We at Zerus know that these are more than just buzzwords. They're really key pieces in building a robust data strategy that starts with a solid foundation. And you can begin building this foundation today and uncovering insights today. And that's what we're here to talk about. So we're really excited to show you our approach and philosophy. If you're not familiar with Zerus, a little bit about us, we're headquartered in West Des Moines, Iowa. And we were established in 1986. So we've got almost 35 years of experience in the technology industry. And of course, things have changed so much through those years, especially now we're seeing the most rapid development yet. So we're set up really nicely to handle those changes and get through any turbulence that comes our way and help our clients through those challenges as well. We've got 6 practice areas that we deal with at Zerus. Of course, today we're talking about data and analytics specifically, but each of those other practice areas you can see on your screen work really cohesively together. And our company is really built on the foundation of trying to solve business problems, not just technical problems. So as we work through each of these really technical areas, we are putting these together in ways that really solve your business problems and answer your business questions with technology as a support. Across the bottom of your screen, you'll see our partners. We're supported by these really heavily, Microsoft, AWS, and Oracle especially in many of our data projects, but we also work with dozens of other technologies to sculpt advanced data solutions in both analytics and engineering. Our speaker today is Tyler Bybee. Tyler is a machine learning engineer here at Zerus. He has a real passion for using data science to solve business problems. And even though we think he's one of the best in the business already, he's currently advancing his expertise with an in-progress master's degree in computer science and data science from the esteemed University of Illinois. Tyler focuses on how implementing and operationalizing machine learning models into everyday processes can solve business problems. He works with Zerus clients to engineer key features and integrate analytical models into their current systems, setting businesses up for continued success and allowing them to focus on gaining insights rather than implementation. So today's agenda, what Tyler is going to dive into us here for, we'll start out with simply demystifying AI. There's a lot of buzz around it, but Tyler will break down what it is and what it does. And then next, getting started today. So a couple quick tools that you can use to find insights with your data. The next topic, laying a foundation, is really the crux of why we're all here today. We'll dive into Zerus foundational framework, which combines the technical and business sides of your data and discover ways to allow your business to uncover insights that will deliver long-term solutions and success. From there, we'll talk about other data science solutions and how machine learning specifically might not always be the answer you're looking for. And then finally, close out with a case study showcasing how cost-effective and quick data science can find solutions for your business. So again, thanks everyone for joining us today. I'm going to turn it over to Tyler to get into the good stuff.
Thanks, Kelsey. Let's jump into demystifying AI. Many of you have heard the most widely used definition of machine learning. It's the ability for a machine to learn without being explicitly programmed. But while this might give you an aha moment for a little while, when it comes to businesses paying actual dollars for a self-learning machine, they tend to come back fairly quickly with some additional questions. Another way it can be described is by mapping a set of inputs to an output. While this is also correct, but it's a little too abstract for us. That's why the basis of my explanation for machine learning today is based more on this definition from Haley Mason, the GM of machine learning at Cloudera. Machine learning is fundamentally learning a function from data. It may sound very familiar because it is, but that foundation that behind all of this is a function, to me, plays much more into a concrete understanding of what machine learning is. Think of all the functions you program. Given these inputs, I need to figure out what to program to obtain my desired output. Now imagine you have that same set of inputs and your desired output and no idea of what the specific steps should be to actually get there. That is the power of machine learning. All it needs is a start and an end, and it will figure out the middle. Let's dig a little deeper. A lot of people's first experience with functions is in algebra. You probably all remember that the idea of a line is just a series of continuous points, and you probably remember that you can describe a line with a function. And this function has a basic framework that all lines adhere to, y equals mx plus b. In this case, x is your input, m and b are the manipulations you make to x in order to get your desired output, y. And all that you need to do to solve for what these manipulations are 2 points on your line. So in this example, we find out this line is represented by 0.25x plus 1, meaning every time an x value comes in, you'll put it through your machine, which multiplies it by 2 and adds 1 to give your output of y a value. But what does this really mean? Let's make it a little more concrete with an example. Say you're wanting to predict the sale price for a particular house given the square footage for that house. The function given for x for this example has been calculated as $10,000 times the number of hundreds of square feet plus $20,000. So a 1,000 square foot house would sell for $120,000 and a 2,000 square foot house would sell for $220,000. But we all know that the sale price of a house isn't only dependent on the square footage. And because of that, we know the data on this plot would look more like this. So how do we start making this function better at predicting the sale price for each house? We introduce more variables. So let's also incorporate the number of bedrooms into each house. And this is the resulting plot this data looks like in 3 dimensions now. Now, the resulting predictions from this model are represented by a plane. Because we're working in 3 dimensions, we can understand this conceptually pretty well. However, we still don't have a very effective model. So what can we do to make it better? More variables, of course. So here we go. Let's include the number of bathrooms and see what it looks like. But already, it's impossible for us to picture in our head. Don't pretend that you understand that 4D cube thing from Interstellar. As humans, we don't have a good grasp or understanding or visualization of more than 3 dimensions. Not only that, but the math now is getting more complicated. We also know that stopping here is not going to be a very accurate sale price either. So if we were actually going to create a model to represent sale price of any given home, aka the Zillow Zestimator, the function would end up looking more like this. And even this is rather simplified. In fact, most machine learning models are calculating across hundreds or thousands of variables, so this brings us back to the original definition of machine learning. If you were to have to explicitly program a function of this complexity, let's just say it wouldn't be a good use of your time. So today, in a lot of businesses, they settle for what they can explicitly program, such as looking across 3 variables to determine which of their customers have the most highest value. Have you heard of recency, frequency, and monetary? Or 2 variables to determine the premium rates for workers' comp based solely on how many employees a company has and what line of work they're in. These are 2 very real examples we have experienced and just recently talking with our clients. But you probably still want to understand a little more about what machine learning is actually doing under the hood. So let's do our 2D example. We have our y and our x-axis and our data. And we want to draw a line that best represents this data. But instead of solving for the variables as we did when we first saw the data, let's do it like machine learning would do, assuming that it's too complicated to simply solve for x. What machine learning does is start with a random guess. After making a random guess for the line, it will score how close all the points are to the line. Use those scores to tell how well the model did overall, and adjust the line based on the scores. Now it looks a bit better, but let's do that process again, and again, and again, until the amount of error stops decreasing in each iteration, and we have the best performance possible for this type of model. So this should give you an idea of why so much data is needed for machine learning. Solving a problem with hundreds of variables requires hundreds of data points to mathematically solve, but to actually make a good prediction on new data, you need multiple distinct examples for every type of variable. So let's take a math break for a second and look at machine learning in one alternative way, like that of a recipe. You can think of the resulting function or machine learning model as a recipe. If you're going to make chocolate chip cookies, the recipe tells you what ingredients you need in what quantities to make them turn out as expected. It's recommended that you follow this recipe to have cookies turn out. Similarly, a model can be thought of as simply a recipe to make a prediction instead of cookies. It tells you how much or the weight of each ingredient or variable is needed to make your prediction. So out of a recipe, you get cookies, and out of a model, you get a prediction. Now, we're always on the hunt for the best chocolate chip cookie recipe. So when you make the cookies, you might realize how slight tweaks or adjustments could improve your recipe. The more times you make your cookie recipe, the better your cookies get. As you make them more and more, you realize that they are better with soft butter or using a little bit of baking soda. As you get more data and train your model more and more, it also evolves. It might realize that the square footage corresponds less and the number of bathrooms corresponds more with the sale price of a house. The more you use your model, the more data collect, the more feedback you get, and the better model you can make in the future. The final thing to mention here is that when you decide to make a recipe, you have a specific food you want to make in mind. You don't go into the kitchen and throw everything into a bowl and see what you can get. You start with an end goal in mind. Whether it's cookies or pot roast, you know what you want to make before you start. Similarly, when you're making a machine learning model, it's a requirement that you know what your goal is or what you're trying to predict. You can't just throw all of your data or ingredients in a bowl and hope that what comes out is what you want. You have to be aiming at something. So what can you aim at? So there are three major types of predictions you can make with machine learning models. The first type of prediction is numerical, or how many. So some examples of these types of questions would be, when will the peaks in traffic be to my site? Or how big will the peaks in traffic to my site be? How many customers can I expect on Black Friday? What is the lifetime value of this customer? So this type of prediction, we call this regression. You might recognize this from a stats course you've taken in the past. The second type of prediction is categories or decisions. This or that. Which of the following is it? So a common use case for this is spam detection. Is this email spam, or is this email not spam or ham? Another example is fraud detection. Is this credit card purchase likely to be fraud or not? Or is this person likely to churn and never return? Or which ad should I recommend out of the 10 ads I have running now online in my retail shop? So this type of prediction, we call this classification. Now, the third example is a little more abstract. In regression and classification, the model is shooting at very specific targets on data that it's trained and specifically labeled. For example, a spam filter learns as people label more and more emails as spam or not, and it helps move them out of junk folders. But this final category is a little different. Based on your data, you might be asking, what is similar or what is different? So types of examples like this are customer segmentation. Everyone's familiar with, okay, so these customers are young and low income, and these customers are old and high income or old and retired. But there's so many more examples in between those that you can help to use to market better. Another would be identifying high-risk patients, outliers. So most of your people might be in one group, but you could have an outlier in many different directions. This type of machine learning algorithm can help you identify those outliers that you don't actually have labels for, but you know they exist. And this we call clustering. So how can you get started making machine learning predictions today? Well, most data scientists work in a programming language like R or Python to explore their data and build machine learning models. But in the last few years, there have been a lot of developments in no-code machine learning tools and model automation. So tools like this one, driverless AI, might look complicated, but once you know a little about data science process, you can easily build predictive models just by telling this tool your target column and how hard you want it to work. There's 3 circles up on the upper right where you basically tell it the accuracy you want, the time it can take, and how interpretable it has to be. And then you can just let it go at your data. So this really allows people to get into machine learning and build effective models just by learning a little bit about, okay, how many iterations, what does this score metric mean, how much time do I have, how interpretable do I need this to be, and what's making the biggest impact. As you can see, variable importance in the bottom middle. It can tell you things like that without you having to code anything. So it's a really, really powerful tool. Here's another tool that is less automated but still has a no-code interface. These can be used both by citizen data scientists for building models without having to know a specific programming language, as well as data scientists to increase their bandwidth. Of course, tools like this require a little more knowledge than a fully automated tool, but there are usually good collection of sample workflows and tutorials online. And at Zerus, we can help you determine what tools would be ideal for your business and get them up and running. But mainly, you don't need a PhD in statistics to get started building machine learning models for your business. Laying a foundation. Deciding on and implementing standardization across your company as your machine learning practice expands is key to finding success. Here are just a few of the various tools and frameworks that can be used for machine learning solutions. And if everyone is on different tech, it's going to make it really hard to scale up. For example, Python and R are very commonly used, as well as SAS and sometimes Java or other products for building machine learning models and exploring your data. We also have various platforms and frameworks to choose from. We have Azure or AWS and maybe Databricks or Spark. And additionally, we have model automation. So how do you want to let your citizen data scientists work, or how do you want to increase the throughput of your data scientists? Do you want to use H2O or a RapidMiner or a data robot? You don't want to end up with some data scientists using one tool and some citizen data scientists using another tool because it's convenient. And then we have deep learning frameworks. So if you're working with things like images or video or sound recordings, you have a collection of different deep learning frameworks to choose from. Your data engineers shouldn't have to worry about being given a random Jupyter notebook and just being told to deploy it and get it into production to make predictions. There should be a standardized method with which the data scientists and citizen data scientists can get their models into use. And that's really the importance of deciding on which tools to focus on. In addition to establishing a roadmap for long-term success with machine learning, standardizing how your company uses data will give everyone a better understanding of how things work together. To do this, we divide the landscape into 4 quadrants. This is our philosophy. When we dive into businesses, a business's data and processes, we have had the most success by following this framework. So we have innovation and exploration, establishing value, core, and expanding understanding and investigation. We'll label the vertical axis questions and the horizontal axis data. And then we'll also differentiate known and unknowns of each of those. So with known data, this is things commonly already in data warehouses or data marts that everyone is using all the time. And unknown data is data that you might have collected in a data lake somewhere, or you're storing it because you think it could be useful in the future, but currently it's not purposed for use. The same thing goes for questions. Known questions are the type of questions you're asking about your data every day or every month or every quarter when you report earnings, or like, for example, it could be, what are our projected sales for this month? That's something you ask every month or every week. And then the unknown questions are what they sound like. You don't know what these questions should be about your data, but you think there might be some insight in the data. So data flows between quadrants from the upper right down towards the lower left and then up. We start with data exploration in the upper right. As we start to understand what business questions need answered, we move down to establishing value. Here we figure out what are the right data sources to answer the questions. We give business value to the data. Now we move to the lower left quadrant because we understand the questions and what data can be used to answer them. In the core quadrant, we apply structure, context, and optimize the data for use. We purpose the data. From here, we move up into the investigation quadrant where we ask, what else can we do with this data? Now let's overlay the user roles of your business onto this framework. First, we have data analysts, data engineers, and data scientists. They spend most of their efforts in the innovation and exploration quadrant working with unknown data to discover unknown business questions, primarily working with machine learning, notebooking, advanced analytics, Python, R, or other exploratory tools. Advanced business users, like business analysts, perform line of business reporting, but they also spend time analyzing data and investigating other ways to use the data to solve business problems, mostly working with known data or known questions. And finally, we have casual business users. They spend the majority of their time with known data and known questions. They don't normally deal with unknown business questions or unknown data. They are the group doing descriptive and diagnostic reporting using tools like Power BI, Tableau, Qlik, and Excel. This group makes up over 90% of users in most companies. Knowing how data moves through this landscape and where different business users work in the data landscape really allows your business to build effective long-term solutions. If you want to learn more about our approach to laying a good foundation for your company's data landscape, look out for our next webinar in the Data Landscape series. Now we can move on to data science solutions. Machine learning and automation isn't always the best solution. Oftentimes, the solution involves making or adding business value to the data by using data engineering to obtain and clean the data for people to use. Other times, it's more exploratory and is more analytics based. It's not so much automation, but instead trying to discover insights. We have worked with many clients who wanted to do machine learning, but the more appropriate and cost-effective solution ended up being related to data engineering or analytics. And this can be seen with our next example, how we were able to get over 10 times return on investment for a project that lasted just a few weeks. And so now we'll move on to that. For a little background on our client, we were working with an urban hospital. Because of their location within a city, they serve a substantial Medicaid population, and their emergency room sees north of 24,000 visits each year. We initially met with them to give some education around advanced analytics and machine learning to help their team understand the value they can have and the types of business problems and initiatives like that can solve. That got their minds working, and so we then had the opportunity to walk them through a use case prioritization workshop to help understand what potential business problems could lead to the biggest overall impact to their hospital. As you can see, the hospital's urban characteristics played a big role in determining the most advantageous use case to tackle. The use case that bubbled up to the surface was around analyzing the usage of their emergency department, or emergency room, as some people say. That was because in August 2018, new state laws and policies were put into effect that allowed for the privatized insurance companies who were covering the state's Medicaid population to no longer fully reimburse the services provided by the hospital within their emergency department if the diagnosis for that ER visit turned out to be a diagnosis that was not considered an emergency. These services could see a reduction in reimbursement up to 50%, and because these were Medicaid patients, the difference in costs were not transferred to the patient's responsibility. Instead, the hospital would just need to write off the reduced payments as lost revenue. As you can guess, especially for hospitals serving a substantially Medicaid population, this could get costly fast. A year after these changes took effect, the hospital wanted to quantify the impact they were having on their bottom line and determine if the analysis of the emergency department data, they could identify ways to minimize the bleeding. The hospital gave us data with their 29 emergency room visit IDs, diagnosis codes, and other related information. Of the 24,000 unique visits to the ER that year, we wanted to understand how many were for non-emergent reasons and what determines if a visit is treated as non-emergent versus emergent. The same Medicaid officials governing the legislation of Medicaid patient reimbursements also established a comprehensive list of appropriate emergent and non-emergent diagnosis codes. If the primary or first listed diagnosis code for a particular visit is on the approved list of emergent diagnoses, then the entire visit and all of the services and procedures tied to it are classified as part of an emergent visit, and therefore reimbursable fully. If the primary diagnosis is non-emergent, then all services for that visit are reimbursed at a lower rate. Of the 24,000 visits to the hospital's emergency room in 2019, 44%, or 10,700, were designated as non-emergent. What we were really interested in, though, was how this affected the Medicaid population, because that's where insurance companies are able to lower reimbursement rates to the hospitals. Of the 10,700 non-emergent visits, almost 5,600 of them were billed to Medicaid insurance providers. So the breadth of this project and how we can really save the money is by focusing on these 5,600 visits, because these are patients on Medicaid who are in the emergency room for non-emergent reasons. To give you an idea of how big of a potential problem this is, the hospital told us that insurance companies could reduce the reimbursement on these visits by up to 50%. So if we assume that for these 5,600 cases, the hospital is getting reimbursed half, we can calculate that they basically have to write off $2.02 million on those cases, which we'll explain more in a minute. So we looked at these 5,600 non-emergent Medicaid visits when we did our initial assessment and found that many of these visits have at least one diagnosis code that was emergent. The team we were working with at the hospital confirmed that only the first listed diagnosis was used in determining if a diagnosis was emergent or not. So they thought. It would be really interesting to know how many cases there were in which the primary diagnosis code was non-emergent, but the second listed code was emergent, so we looked into that. We found that 1,424 of them had an emergent diagnosis as the second listed diagnosis, 25% of all non-emergent Medicaid cases. So what does this mean? We wanted a better idea of what was happening in these cases. So here's an example of a patient going to the emergency room with a complaint of chest pain. And here's what she was diagnosed with. The first diagnosis listed was not emergent, and that is just other specified diseases and conditions complicating pregnancy. So what we have is a pregnant woman who went to the emergency room primarily for reasons that are not deemed an emergency according to the new regulation. So that means right away that the whole visit is classified as non-emergent and will be reimbursed at a lower rate. However, if we look at the rest of the diagnoses assigned, we can see the second diagnosis, chest pain, is emergent. Then a few other emergent diagnoses like upper right quadrant pain and epigastric pain. And finally, we see that she was suffering from carbon monoxide poisoning. So this is a really good example of the type of situation that would be valuable for them to review in a real-time dashboard. So getting back to some of the dollar amounts we talked about earlier, here we can see if we look at the Medicaid patients visiting the ER with emergent diagnoses in the first row, the average amount charged to Medicaid is $2,500, and the average amount paid by Medicaid is about $750, which works out to a 29.7% reimbursement rate. But then, if we look at all 5,600 non-emergent cases in the next row, we can see that the average amount charged is less at about $1,700. However, we also see they are reimbursed just $360 out of that $1,700, which works out to an effective reimbursement rate of 21.1%, much lower than for emergent visits. If we take this $361, which is about half of what they used to be getting reimbursed, we can multiply it by that 5,600 non-emergent visits, which works out to $2.02 million we spoke about earlier, that the hospital just has to write off. So now, what's really interesting looking at the first row is that if we look at, or at the third row, sorry, if we look at the 1,424 cases in which the second listed diagnosis is emergent, not even cases where there's an emergent diagnosis somewhere, but only in the second position, they have a slightly higher charged amount than actually emergent cases at $2,600. But they have a lower reimbursement amount at $520, which means the effective reimbursement rate ends up being even lower at 19.8%, as you can see in the bottom right. So it ends up being that in cases that actually should be emergent, they're getting significantly less than they should be at 29.7%. So what we did was upgrade the reimbursement rate from 19.8 to 29.7%. That would increase the $500 to $780, which is a difference of $260. We can then take that $260 times 1,424 patients, and we end up with over $370,000 of recoupable revenue they should be getting, and they could be getting back. When we presented these findings to the hospital, they couldn't believe how much money was being left on the table, and they thought all of our analysis made total sense. Obviously, assuming that you could switch the primary and secondary diagnosis on all 1,400 of those past visits and appeal them isn't really realistic. But they said most of the time they could easily be switched in the future. They saw this as not only a case of additional revenue, but also as a chance to work with billers to place the emergent code as the primary code where possible. Which is why a lot of our recommendations were to help them implement systems to do this more proactively, rather than to have to appeal previously submitted claims. In summary, we've covered a little about how machine learning works. It's not magic, it's just a combination of math, stats, and data. You don't need to hire someone with a PhD to do it successfully. There are some really powerful no-code tools that can be used by people with a bit of knowledge in the data science process. Also, laying out a foundation will give you the best chances of long-term success. And as we just spoke about, AI isn't always the best solution. There are a wealth of solutions that aren't related directly to machine learning automation, but are related to data pipelines or data analytics. With that, I'll move on to the next steps I can take and hand it off to Kelsey.
Awesome. Thank you, Tyler. I love that hospital story. I think it's really exciting. So if our listeners feel the same way, there's a couple next steps that you can take to continue to learn more or even to dive right in. So the first bullet here, our machine learning and muffins, is a breakfast session. You can find more information at zerus.com/breakfast. But here we come in and bring your team breakfast, provided you're in the office. Currently, we can do virtual options like our webinar here. But we'll come in and really dive into machine learning for your company. So we love this session because it's really personal. So we will talk to you beforehand and discover what your questions are or what problems you're facing right now, and give you a presentation that hopefully addresses those and allows your whole team to ask additional questions as well. If you think, we're good on that, we kind of have a good understanding, we're ready to dive in, then check out Spark at zerus.com/spark. We say it only takes a spark to ignite a whole flame. And actually, this hospital story that Tyler just shared with us was a Spark engagement. So the purpose of this is to get started right away and get some quick wins and deliver pragmatic next steps in as little as just 2 weeks. So with that, we want to open it up to some questions and discussion. At the beginning, I mentioned you can submit some questions, and we do have a couple here that I'll read to Tyler to get you your answers. So the first one, Tyler, we have is, what resources can I find and send to my team to start with some analytics training?
Oh, good question. So, of course, I would recommend machine learning and muffins would be a great way to learn some more about machine learning. But another really good resource we found for some more education around machine learning is, what's it called? I think it's called AI for Everyone. It's a Coursera course led by a really prolific AI expert. But yeah, I think it's AI for Everyone on Coursera. It's a really good, pretty good high-level overview for how machine learning can be applied as well.
Awesome. So we talked about our hospital case study. It sounds like we've got a couple of people in, industries other than medical. So what are some other industries you've worked in, and do you have some use case examples for how advanced analytics apply to those industries?
Okay. Yeah, we've worked in a wide variety of industries. Some of the more notable ones, I suppose, I don't know. Manufacturing is one industry we've worked with, and so that was trying to predict when machines were likely to fail. So that was a very direct machine learning problem or answer solution. Another industry we worked with was insurance, and that had to do with predicting the category a claim would fall into given a specific set of criteria. Those are some of the bigger ones we've worked with.
Mm-hmm. Awesome. Thanks, Tyler. Let's see. So we've got one. How do you find success with your client data, even if you aren't highly knowledgeable about that data?
Okay. Yeah, so there are really two parts to this question. The first I would say is that we work closely with clients. So when we worked with that hospital, we would meet with them every week and discuss what we had found in the previous week, and they would give us some insights. And we really dive deep into getting the systematic knowledge your company has from you by working with you. Additionally, we work, of course, with feature engineering, if you've heard of that, which involves imparting a lot of that business knowledge into your data. So, for example, dates. Dates are a big one. If data is a column in your data set, like, you implicitly know a ton of information about that date. Maybe your company has way more claims on Mondays than it does over the weekends, or maybe Wednesday is your busiest night of online retail sales or something like that. But the machine doesn't recognize dates in nearly as many ways as humans do. So feature engineering allows us to impart many different categories or I guess types of information about just one column. So it might look like you just have a little data, but really with some feature engineering, you can really get a ton more useful information out of your data.
Yeah, and I think that's such a good example of, like we talked about earlier, how we can use these really technical concepts and practices to answer business questions and really lay out what we need to find and partner with our clients to make sure that we're finding the answers that they need. And our last question that came in is a little bit similar. So we've got someone who it's kind of asking more about that business side. They're in their marketing department at their company, and they've asked, or they've mentioned that you gave a couple examples of some quick win tools earlier, speaking to like the H2O tool. So they're saying, I'm in marketing. A lot of marketing tools come with built-in AI offerings. Should we be using those built-in tools for our marketing program, or should we look to our data team to help us build a more holistic approach?
Oh, good question. So, those built-in tools can be a really good way to get started, but it might not give you like the exact answer you need. Or it might give you something close or something better than you had before, but it's very likely it won't be the specific and the answer to the specific question you want to ask. Now, incorporating a lot of data into these third-party tools can be hard, which is why it's really important to lay a foundation and figure out how everything works together. But that is why we've partnered with companies like Marketo and Telium, because they really do focus on getting all of your business data together into one spot so it can be used by these solutions. It's not so much an integration problem anymore as it is a machine learning problem once you have all of the data where it's useful. And again, back to those built-in tools, a lot of times those built-in tools only have access to the data that they have access to. It's hard to give them access to more data, or it's hard to integrate that data into some of those predictive built-in features they have. Yeah.
Yeah, thanks, Tyler. I think that question is something we hear a lot, or people in different business departments kind of asking how to use their data. And I think it's just a perfect example of how we tie our data analytics practice into our other practice areas. So if you want to learn more about that, please reach out to us. I'm going to leave this screen up for a few seconds. You can take a screenshot. If you've got other questions that you think of later on, shoot Tyler an email. Shoot us a contact form on our website at zerus.com/contact. Otherwise, be on the lookout. Like Tyler mentioned earlier, we're working on another webinar in this series. We've kind of introduced advanced analytics, and to build a really strong foundation that's going to take you years into the future, you might need some data engineering to go along with that. So our next webinar will be on data engineering with our Director of Data Engineering Services, Justin. So we'll be sending that out. We'll be sending out the recorded version of this webinar, so you can share that with your team if you'd like to. And again, check out Machine Learning Muffins and Spark at the links on your screen, and send us any questions in the meantime. Again, we appreciate everyone being here today. This was really fun. We're so glad you could join us, and we hope that you have a great rest of your day.
Thanks, Kelsey. Thank you, everyone.
Thanks, Tyler.